And so isolation and purification of proteins is really important in the lab, but it's not also important just for research. It's very, very important clinically, especially the identification of proteins. In hospital laboratories, diseases are often diagnosed by quantifying and looking at the presence of particular proteins, whether that protein is an Ebola protein or whether it's troponin for heart disease diagnoses or whether it's hemoglobin levels, right, to look for anemia. There are a lot of assays performed in hospital laboratories to diagnose disease based on protein levels. Now, before we talk about protein separation and protein identification, it's going to be important for us to talk about protein charges because we're going to separate proteins based on their charge. So we're going to have to be able to predict protein charges at different pHs, and we're going to think about it first by thinking about what's the charge on an amino acid, and we'll start with the simplest amino acid, glycine. Well, we already know that all amino acids have an amine group and a carboxylic acid group, and if we look sort of at a titration curve that we have over here of glycine, we can think about what is the charge, overall charge on glycine under different pH conditions. Now, if we look at this titration curve, we see these two sort of level areas where we are reaching a particular equivalence point. And these two level areas really describe the equilibrium as we go from a weak acid to its conjugate base. So down at low pHs, around 2, we see the transition of this carboxylic acid group from its acid form to its conjugate base form. This is an equilibrium between these two molecules, and that equilibrium can be described by a Ka value, and that Ka value has a particular pKa, right? Now, we know, according to Henderson-Hasselbalch equation, is that when we have an equal amount of the base and the acid, then the pH is going to be equal to the pKa. So if we think of this as the pKa value right here, we know that at that pH we have an equal amount of the acid in the base form. Now, what are the charges on these? Well, I would look at the acid form and I'd say, well, it's got a net positive charge. The conjugate base form is net neutral, right? It has a positive charge and a negative charge, but they cancel each other out. Now, this equilibrium isn't the only thing going on in glycine or other amino acids. We also have another equation up here that describes the amine group acting as an acid. Now, this occurs at a much higher Ka because an amine is obviously not as good of an acid as a carboxylic acid. But we can see the amine group losing its proton. There's an equilibrium here and a Ka value associated with it. This molecule, the acid form, I would say is neutral. It's actually the same molecule as this down here. But then when we form our conjugate base, this is a negative, right? So when we think about the ionization states of glycine, the first conclusion we could probably make is, well, it depends on what pH this glycine is existing at. If it's a very acidic pH, then we're going to have a lot of positively charged glycine molecules. If it's sort of a middle range pH, we'll have a bunch of neutral glycines. And if it's a very, very basic pH, we're going to tend towards a negative ionization state. Now, this is just glycine. Other amino acids, some of them have R groups that can also act as acids. Serine, glutamic acid, asparagine, things like that. And so they're often not just the two pKa values for the carboxylic acid and the amine part of the core of the amino acid. There's sometimes another pKa for the R group dissociation. Okay, so this is just for an amino acid. And one way we're going to think about the overall charge of a protein or any molecule is to use this term called isoelectric point. Isoelectric point, or I'll try to draw this out. This is also called the PI value. Now, the PI value is a useful way to think about the overall charge of a molecule. And the definition of the PI is the PI, or the isoelectric point, is the pH at which the net charge on the population of molecules is neutral. Okay? If we go back to our look at glycine, we can say that the PI is this middle pH right here, right above 6, where we're going to have an equal amount of positive and negative charge on our glycine, and overall the population of glycine in our sample is going to be neutral. So right here, this slide says the pH or the PI values right at 6. That's when it's neutral. Okay, now that doesn't mean that there's no charge on the molecule. It just means it balances out. So the net charge is neutral. Now, what happens if we are at a pH that is not equal to the isoelectric point? Well, it means that the overall charge on our molecule isn't neutral anymore. So if our pH is lower, that means we're in a more acidic environment, and our charge on our molecule is going to tend to have a net positive charge. If we move away from the isoelectric point to a higher pH, which is more basic, then our molecule is going to tend to have a more negative charge associated with it. Okay. Now, this prediction of what the charge of a molecule is going to be with relationship to its PI value is going to be very important as we try to isolate proteins based on binding to positive and negative charges. So we've just talked about amino acids, but let's extend this to think about proteins. Let's imagine this big long line here is just a big long protein. Protein charges get really complicated, right? The amine group and the carboxylic acid groups are tied up in the peptide bonds of the protein, so we usually don't think of those as being charged, except, of course, at the N terminus and the C terminus of the molecule, where those are free to be reactive. But there's a bunch of R groups present on these amino acids, so these pK3s, these pKa3 values can, the R groups can be positive, negative, or neutral. And so when we try to titrate a protein, we don't see these nice, distinct level places where we can look at a particular dissociation of one atom coming on and off. We get this sort of smeary titration curve, but we can think of each protein as having an isoelectric point, a PI value, where that protein has a net neutral charge, and that's really, really useful when we start thinking about complicated things like proteins. So let's look at an example here. If we go and let's just look up the alpha subunit for hemoglobin, right? Let's look at its amino acid sequence. Here it is. This is just the primary sequence of hemoglobin, alpha subunit, starting with a methionine, ending with an arginine. I can copy this, and I can go to another program where it will look at the different R groups of all the amino acids that I've input here for hemoglobin, and it will predict a PI, right? It will predict the isoelectric point. So let's see what it says. It says I've got a pretty high PI of 8.72. What does that mean again? It means that the alpha subunit of hemoglobin, while there's lots of charges all in these R groups, if this was at a pH of 8.72, there would be a net neutral charge to the protein. All those charges would cancel out. Now, on a side note, it also tells me the molecular weight, the MW, for the protein. So let me just mention this because we'll see it often in the future. The molecular weight for the alpha subunit of hemoglobin is 15,257, right? That's in grams per mole. So in biochemistry, these big polymers like proteins are big, right? We're used to thinking of molecular weight of atoms in introductory chemistry or in organic molecules as being in the hundreds maybe of grams per mole. When we've got big things like proteins, they're in the thousands of grams per mole. And this is a really kind of small protein anyway. It's only 142 amino acids, and it's got a small molecular weight of 15,000 grams per mole. We often describe molecular weight of proteins in kilodaltons. A kilodalton is just 1,000 grams per mole. A dalton is a gram per mole. So this is around a 15 kilodalton protein. Again, not that big, right? We'll see some monster molecules in metabolism that have millions of grams per mole molecular weight. Okay, but back to PI. Let's remember this. Here's our PI, 8.72. What does that mean? It means if we had this hemoglobin protein at a pH of 4, then the protein would have a positive charge. And if we had this protein at a pH of 10, something more basic, then it would have a negative charge associated with it. Now let's think a little bit about how that works. Let's say this is hemoglobin, and we're going to try to figure out what's going on with it. Okay, so let's say the PI of this, PI, what was that, 8.72? 8.72. Okay, 72. So at a pH of 8.72, there would be charges on this molecule, right? But they would balance out. So we would have a net neutral charge. Okay. Now, what would the charge of this protein be at a pH of 4? What would the charge be? Well, the charge would be positive. Okay, and the way you can maybe think of that instead of just memorizing it is saying, well, if I know that at a pH of 8.72 that I have a net neutral protein, if I put it at a pH of 4, this is a more acidic environment. And if I have a more acidic environment, that means I'm going to have protons sort of bombarding this protein. Now, what will the bombardment of this protein with acidic protons do to the charge? Well, let's take maybe one of these negative charges and break it down a little bit. Maybe this is a carboxylic acid that's been deprotonated with a negative charge. Well, what's going to happen to that negative charge in a more acidic environment? That negative charge will become neutral, right? So we're going from negative to neutral. We're really becoming more positive. Okay, another functional group we can think about being modified in the more acidic environment is an amine group, right? We can protonate that NH2 to form NH3+. We're going from neutral to positive. So if we bombard our protein with positive protons in a more acidic environment, we're going to tend to make this negative neutral, this neutral positive. We're going to tend to make our protein more positively charged. Now, if we put this at a pH of 10, the opposite of these reactions are going to occur. The pH of 10 is a more basic environment, so it's going to tend to remove protons from my protein. Therefore, things like NH3+, we're going to remove that proton, make it neutral. Protonated carboxylic acids are going to become negatively charged. So if we had a pH of 10, our charge would be negatively charged. Okay? So it's important to be able to look at the PI for a particular protein and say what its overall charge is going to be at a pH, because we're going to use those charges in order to isolate those proteins.